In this lecture, we take a look at a detailed example of the kinematics of simple harmonic motion. In my last lecture, I developed the following expressions: position, velocity, and acceleration as a function of time. Let's go ahead and use these expressions in the following example. Please copy it down into your notes as I read it here. So in SHO, a simple harmonic oscillator has a position function that's given by the following. So x of t is equal to 3 cosine of the quantity pi over 4 times t, and it's in terms of meters. Okay, in part A of the problem, we're just merely to graph out position, velocity, and acceleration as a function of time. So let's immediately go ahead and do that. In order to do so, however, let's go ahead and identify the various quantities that we have here for this oscillation contained within the position function. So first of all, the amplitude is given to us as 3 meters. That's always the coefficient in front of the cosine. And then we also have omega, the coefficient in front of time t here in the argument of the cosine function. Omega, the angular frequency, is given to us as pi over 4 radians per second. And then immediately from here, we can calculate the following quantities. So first of all, recall that omega is equal to 2 pi divided by the period. So if you cross multiply, you can then calculate what the period is. We're going to need that for our graphs. So the period is 2 pi divided by omega. So 2 pi divided by pi over 4 ends up being a total of 8 seconds. And then if necessary, we could also calculate the frequency, which is the inverse of the period. That's 1/8 hertz. So 1/8 of an oscillation occurs per second. Obviously, this oscillation is very slow, but I'm just using easy numbers to work with here for this numerical example. Okay, let's go ahead and graph out, first of all, the position function. That's just our cosine curve like so. So we have position in meters as a function of time t in seconds, using a different color. Right here is our cosine like so. Typically, what we always do is we always graph out one full oscillation. So then therefore here along the time axis is one full period of 8 seconds. And then here and here, the amplitude positions of 3 and -3 respectively. Okay, and then let's go ahead and write down the velocity function and then graph that out. So the velocity function, v of t, is equal to negative a times omega, and then times the sine of omega t. Okay, now here's how the units of this quantity work. First of all, there are no units associated with trig terms, because recall that ultimately trig terms are just ratios. So all the units come from the quantities here in front of the sign. The 3 is in terms of meters, and the pi over 4 is in terms of radians per second, which is just per second in terms of the units. So ultimately, we end up here with meters per second, as we should. Okay, the maximum speed of the oscillator, this occurs when the oscillator passes through the equilibrium position, and the coefficients 3 pi over 4 meters per second. Okay, let's go ahead and graph this out. Okay, so time in seconds, velocity in terms of meters per second, and then once again, we graph out here one full oscillation. In this case, we're graphing out a negative sine curve, which if you recall looks like this. This is one full period of 8 seconds. And then here and here are the maximum speeds plus and minus 3 pi over 4 meters per second. Like so. Okay, and then lastly, in terms of the graphs, is the acceleration function. So the acceleration function is negative a times omega squared. So that's pi over 4 quantity squared, which is pi squared over 16. And then multiplied by cosine of omega t. Like so. And now here's how the units work. We have the 3 in terms of meters, and then the pi over 4, which is being squared here, is in terms of per seconds squared. So you end up with meters per second squared as the units of the acceleration, as we should. And then we'll just graph out this negative cosine function like so. So once again, time in seconds, acceleration in terms of meters per second squared, and then our negative cosine function merely looks like this. Once again, here's one full oscillation, so this is a full period here of 8 seconds. And then here and here is the coefficient 3 pi squared over 16, which is the maximum acceleration of the oscillator. The maximum acceleration of the oscillator occurs at the endpoints, that is, at the amplitude positions, because that's when the spring force is the greatest value. So we've got positive, 3 pi squared over 16, and then negative, like so. So all that we've really done thus far is we've just identified various things in the functions and then graphed them out. Okay, let's take a look at part B and then the remainder of the problem, which is related. It says, when is the oscillator at a position of -1 meter? So let's go ahead and take a look up here on the top board at our position graph. And then right here, for example, is a position that's positive, that we need negative. We need -1 meter like so. So then therefore, what's being asked for in part B of the problem is this time here and this time here. Notice that the oscillator is in a position of -1 meter twice per oscillation. We have to find those two times. So in order to do so, what I'm going to do is take the position function here, set it equal to -1, and then in radian mode on my calculator, I'm then going to solve for the time t. Okay, now I don't need some things here, so let's go ahead and get rid of these quantities like so. And now what I do is I take my position function and set it equal to -1. And then I run through the algebra here to solve for the time t. So divide by 3 to the other side like so. And then in order to get rid of the cosine on the right-hand side of the expression, what we do is we take the inverse cosine of both sides. So inverse cosine of the left-hand side equals then inverse cosine of pi over 4t, which is just pi over 4t. And then in order to solve for the time, as I said, you do have to be in radian mode on your calculator. So making sure I'm in radian mode, and now what I do here on the left is inverse cosine of -1/3. Okay, I'm going to write down the number that I obtained here such that you can check yourself as you work. It's about 1.91. And then I'll just cross multiply now to solve for the time. So times 4 divided by pi, and that works out to be about 2.43 seconds. I'm going to call this time here t1. 2.43 seconds, and that's pretty obviously this time right here, because the halfway point would be 1/2 of 8 seconds, which is 4 seconds. So this guy right here is t1. Now, because the cosine curve is symmetric, what I can do now is use a little bit of symmetry in order to find this second time here, t2. So recall the symmetry here of this cosine curve in the following way. This distance here, if you will, along the time axis is the same thing as this distance here. So if this time is 2.43 seconds, then the time t2 is going to be 8 minus that value. Now, just simply saying by symmetry, that's perfectly fine. We would then write the second time t2 as being equal to 8 minus 2.43. So 8 minus 2.43, let's do the math here properly, works out to be 5.57 seconds. So that's this second time here, label it as t2. Okay, let me move my file. Okay, now for the remainder here of the example, we'll take these two times and find the velocities and accelerations at these two times, and then we'll also mark those points correctly on their respective graphs. Okay, now first the velocities. In order to find the velocities at these two times, all that I have to do is take the two times and plug them here into the velocity function. When I do, I expect to get the same speed for each time. The kinetic energy should be the same at this position here of -1 meter, regardless of which direction the oscillator is moving, but one of the velocities will be positive and the other will be negative. So let's go ahead now and find v of 2.43 seconds and then v of 5.57 seconds. Once again, I'm in radian mode on my calculator when I do this. So what I now type in is -3 times pi over 4 times the sine of pi over 4, there we go, pi over 4 times 2.43, and this works out to be -2.22 meters per second. Okay, before I mark it, which as you'll see is probably the trickiest part of this problem, let's go ahead now and find this velocity. It should be the positive value. So -3 times pi over 4, then multiplied by the sine of pi over 4 times 5.57, and that works out to be positive 2.22 meters per second. So if you get to this point in the problem where the two numbers here are the same of several decimal spaces, then you've done the problem correctly thus far. And now I've got to mark these points here correctly on this graph. So first of all, 2.43 seconds, we have a velocity of -2.22 meters per second. So down here is -2.22 meters per second or so, and then therefore the time t1 of 2.43 seconds, is it here on the left or is it here on the right? It's here on the right. And the reason for that is as follows. Let me get a ruler to illustrate. In this problem, think of this as the equilibrium position. We're given that the position of the oscillator is -1 meter. This means that it's to the left-hand side of the equilibrium position. However, this then means that the spring force, and then therefore the acceleration, is back towards the equilibrium position in the positive direction. That is towards the right-hand side. So right here at this point, notice that the slope of the tangent line, the slope of the ruler's edge, which represents the acceleration, is a positive number. That's not the case over here. Over here, notice that the slope of the ruler's edge is a negative number. That cannot be when the position is negative. When the position is negative, the acceleration has to be positive. So then therefore, right here at time t1, we have a positive acceleration. Watch me use the same reasoning for the second value. Positive 2.22 meters per second, that's up here like so. And then we've got our time of 5.57 seconds, t2. Is that here on the left, or is it here on the right? It's here on the left for the exact same reason. Once again, if the position of the oscillator is -1 meter, the acceleration has to be a positive number. Notice a positive slope here for t2, just as I had earlier for t1. Notice that the two slopes are the same. So now when I calculate the acceleration, I should get the same positive value for both. So now let's see. We go over here, and we plug in 2.43 and 5.57. I should get the same positive number for both of these times. Let's see if I do. All right, so just be careful of negative signs here as we work. So -3 times pi squared over 16 times the cosine of pi over 4 times 2.43, and that works out to be a positive value of about 0.61 or so meter per second squared. Now I should get the exact same number for the other time. So -3 times pi squared over 16 times cosine of pi over 4 times then 5.57 seconds. And sure enough, I get the same value, 0.61 meter per second squared. So 0.61 is roughly here or so, and then therefore here's t1 and t2. These two times here are easy to mark on this acceleration graph. One way to check yourself when you reach the end of the problem is to note the following. Notice that the acceleration graph is essentially the negative of the position graph. And the reason for that is because the position graph is a cosine and the acceleration is a negative cosine. Okay, now in this example and in everything that I've described thus far about the kinematics of simple harmonic motion, we always started the clock specifically when the position of the oscillator x was equal to positive a. That doesn't necessarily, however, always have to be the case. So mathematically, what happens if you start the clock at a different point in the oscillation? I'll get to that in the next lecture.